Lava lakes are rare on Earth, but there is actually somewhere in our solar system where lava lakes are incredibly common. This somewhere is Io.
But before we jump right into lava lakes on Io, figuratively, I am super excited to thank the sponsor of today's video, Skillshare. Skillshare is an online learning community with thousands of inspiring classes for people just like you, people who love to learn online. So stick around to the end of the video to hear more about Skillshare as well as a special offer I have for you guys. Okay, back to Io.
Io is one of the four largest moons of Jupiter, called the Galilean moons or Galilean satellites because Galileo discovered them. And these moons include Io, Europa, Ganymede, and Callisto. But Io is the only one of these that's got high temperature volcanism like we have here on Earth, but it's even more volcanically active than Earth is. We can see down here in the globe images all these volcanic features and amazing colors that the volcanism on Io creates because of what it's made of, which I'll talk about in a second. And we can also see to the right this big plume of material coming off Io, and there's many images of many plumes like this coming off of Io to incredible heights and even supplying material to other nearby moons. So Io is pretty important not only in the context of volcanic activity on its own, body, but also for supplying material to other Galilean satellites, as well as giving us a great understanding of how tidal heating works in our solar system. And tidal heating, if you don't know, is how Io is heated and how it maintains such a volcanically active state. And I talk about that in my first Io video, where I talk about more of the background behind Io. This video is going to be more focused on the lava lakes, but I will have one slide where I will have just a quick overview of tidal heating. So if you don't know what it is, don't worry, it's coming. So again, Earth and Io are the only two bodies in our solar system where we've observed active high temperature volcanism. And the colors that we see on Io are due to what the volcanism or lava is made of, which includes silicate volcanism like we have here on Earth, which on Io appears black or dark in color, but also sulfur volcanism, which appears yellow, also this orangey red color, the white sulfur dioxide frosts. There's a bunch of different colors on Io just because of the immense quantity and variability of sulfur compounds on Io. And in today's video, we're going to be talking specifically about lava lakes on Io, which in some cases resemble calderas on Earth, but are also still very unique to Io in many ways. And a lot of these unique qualities of Io's lava lakes, or what's called Paterae, are still mysterious. We're still not sure why they are the way they are, how they form, and all these things. But we have hypotheses, and that's what I'll be talking about today. So just for a little Paterae background, Paterae is kind of the word they use for lava lake, or kind of like the volcanically active regions where sometimes lava lakes are present on Io, and I'll kind of explain the sometimes part of that in a future slide, because not all of these Paterae on Io are lava lakes or contain lava lakes. Some of them are more so lava ponds, which I'll explain. Don't worry if you don't understand that. We'll get to that. But just for some general background, Paterae are the most common volcanic feature on Io. We can see the largest of Paterae on Io is Loki here, this black thing. It's got like an island in the middle, and the rest is active volcanism. And in terms of morphology or geomorphology, kind of the shape and structure of these Paterae, they are unique to Io. Like I mentioned, there are some similarities to calderas on Earth and even Mars and Venus, because Mars and Venus at one point had volcanic activity, and there are some similarities between all of these calderas on these different volcanically active or previously volcanically active bodies. And for example, we can see the Massawa Patera on Io is somewhat similar to the Mauna Loa caldera on Earth and Hawaii, as well as Olympus Mons on Mars. But there are many dissimilarities, especially among the different Paterae on Io. So we'll talk about what those are and why that might be throughout this video as well. For example, one dissimilarity between Io's Paterae and active lava lakes versus Earth's lava lakes is the pure amount. There are over 500 Paterae on Io, but lava lakes on Earth are incredibly rare. The Paterae on Io also seem to have some correlation with mountain building on Io. 41% of mountains that we've observed on Io are adjacent to Paterae. This might be because magma can ascend the faults that are associated with the mountain building, but we're still really not sure exactly how the mountains form on Io and what this correlation between mountains and Paterae means, because the mountains seem to have a correlation with Paterae, but the Paterae don't seem to have a correlation with mountains. Now, that might sound a little weird, but it just means that many of the mountains, 41%, are adjacent to Paterae, but there's so many Paterae that represents only 13% of Paterae. So in other words, only 13% of Paterae are adjacent to mountains. So it clearly doesn't require that there's mountain building and faults in the area for a Patera to form, but it does seem to have some correlation where the mountains are forming with the Paterae. So there's a lot still up in the air and unknown about these correlations and such that we're observing. Another difference between Io's Paterae and Earth's lava lakes and or ancient calderas is the size. The sizes of Paterae on Io are huge. The mean diameter, the average diameter of Paterae on Io is 40 kilometers, and Loki, the largest Patera on Io, has a diameter around 200 kilometers, whereas on Earth, the largest caldera is Yellowstone, which has a diameter around 70 kilometers, and most calderas on Earth are much smaller than this and the ones on Io. Additionally, Paterae on Io have much more irregular margins than on Earth, it seems, and that's around 42% of Paterae that have these irregular margins, and only 8% are found on low shield volcanoes, which is probably the most significant difference compared to calderas on Earth. So calderas on Earth are associated with or are on low shield volcanoes because of the way they form, which I'll explain step by step later. However, that's not the case for Io's Paterae, which indicates that they form by a completely different mechanism, which I'll also talk about our hypotheses for how they form in a later slide, step by step. So that's coming. But first, let's talk a little bit about the Paterae distribution on Io, because there are some correlations here that we need to discuss because they might indicate something about the interior of Io. Many Paterae are found at low latitudes between 25 degrees north and 25 degrees south, as shown by the rectangle here on the map of Io. And there are less Paterae at the poles of Io, but the Paterae at the poles are larger in size. Why this correlation between size and latitude? Well, we think it might be due to thicker crust at the poles, leading to a lower abundance of Paterae, and deeper magma origin and larger eruption volumes, leading to larger Paterae. But there's also a correlation with longitude, it seems. It seems that the Patera distribution peaks at longitudes 330 degrees west and 150 degrees west, as shown by the regions on the map here. And this is possibly due to the direction of Jupiter's greatest tidal stress or tidal effect on Io, but we're not totally sure about that. The latitude trend seems to be more obvious than the longitude trends, so that's still kind of a work in progress in terms of our understanding of why these latitudinal and longitudinal correlations exist. Paterae also play a major role in terms of heat transfer on Io and from Io's interior to its surface. And we can actually see the heat transfer or heat flow or loss from these different regions on Io, with the red regions being the most heat flow and the green ones being less. Some of these heat spots are really consistent in the continuously active Patera, especially Loki, which we'll talk about in a second. But before I do, like I promised you at the beginning of the video, I do want to talk a little bit about tidal heating, just to remind you what it is before we move forward, so that you know why Io is so hot, even though it's so far away from the sun in our solar system. So it clearly doesn't receive a lot of solar heating, but it does receive tidal heating. And tidal heating just means that because it undergoes so much tidal stress as it orbits Jupiter, because of Jupiter's massive gravity and pull on Io, that stress causes it to stretch and change shape as it orbits. And also because it's not a circular orbit around Jupiter, it's not at a constant distance from Jupiter, and so it's elliptical orbit, which means that sometimes it's closer to Jupiter, sometimes it's further away, and that also creates, stretching and compressing and all these things forces that are keeping Io extremely hot and volcanically active. And it's not just Jupiter that's pushing and pulling on Io, it's also the other moons that are orbiting Jupiter that also have a gravitational effect on Io and therefore a tidal effect. So all these tidal effects are pushing and pulling Io in every which way and stretching it out to the point that it remains incredibly hot and active. And the Paterae on Io are not only the most common volcanic feature on Io, but also play perhaps the major role, the largest role in heat transfer from Io's interior to its surface, and therefore heat loss. And Loki alone accounts for 10 to 20% of Io's total heat loss. And we can see kind of another version of this heat loss map or heat transfer map where we have 1 to 10 gigawatts of heat shown by the blue dots, 11 to 100 gigawatts by the green, 100 to 1,000 by the yellow, 1,000 to 10,000 by the red, and over 10,000 gigawatts shown by the black. And so all these regions or hotspots on Io are contributing to heat loss on Io, and many of these represent Paterae. However, Patera formation and resurfacing mechanisms are not well understood, and they seem to vary across different Paterae, and so it's not a consistent mechanism. For example, Loki might have formed and might maintain its activity in a different way than other Paterae on Io. And so let's talk about what these Paterae might represent and how they might have formed and what style of activity or mechanism of resurfacing is going on these various Paterae and how it might differ across different Paterae. So Paterae might be lava ponds or lava lakes, like I mentioned earlier. Lava ponds could be just depressions filled by lava flows across Io's surface, and lava lakes are probably fed directly by magma chambers below or some sort of magma source below them, and then resurfaced by crust replacement across the lava lake because of the direct source of magma below. Long-lived Paterae such as Pele and Loki are likely these directly connected lava lakes that are continuously active over decade-long timescales, and that's probably because they're directly connected to a magma source below. Other Paterae on Io might have formed very differently and might maintain their activity very differently as well. For example, Prometheus Patera likely overflowed within its Patera, and then that caused a lava flow to form adjacent to the Patera, whereas the Pilan Patera may have formed in an opposite way, where a lava flow spilled into the Patera. One thing we look at to try and understand how Paterae on Io form is their morphology, or kind of shape and structure, and their geological context overall. But before we get into Io Paterae formation, let's talk a little bit about how ash flow calderas on Earth form, since they're the closest analog in terms of morphology to Io's Paterae. These ash flow calderas, as we can see in the figure to the right, form via sudden eruptions along ring fractures, and these are just fractures within volcanoes that cause magma to ascend and erupt out of that volcano, and all of that material loss from that volcano causes then a collapse because it's no longer material that's underneath the volcano, and that area then collapses into itself, and that causes the caldera to form. And that's also why the calderas on Earth are kind of on low, broad shields where there's a rise and then a dip in the middle where the caldera is. But unlike calderas on Earth, Paterae on Io seem to be inserted into flat plains. So flat plain and then dip, and that's the Patera. There's no broad shield rise around the Paterae on Io. And this flatness may be due to the lower viscosity of lavas on Io, and therefore completely different eruption styles and potentially even formation mechanisms. But there are other ways that calderas on Earth can form. For example, incremental collapse into a partially drained magma chamber. So basically, this means the caldera formed in a region where there was never even an eruption because the magma chamber that was beneath the region that would have erupted and formed the caldera was drained from below and potentially erupted in a nearby region. And then that material loss from below in the magma chamber causes that region that didn't erupt erupt to collapse and form a caldera. And many of Io's nested paterae, such as the Masa, Tavashtar, and Gishbar paterae, resemble these incremental collapse terrestrial and Martian calderas. And so these may have formed by the drainage of magma below rather than eruption of material and then collapse because of material loss out of the surface. But that doesn't necessarily explain away the flatness of other paterae that clearly have and do continue to erupt. So now we're starting to see all the differences between Earth's closest analog, ash flow calderas, and Io's paterae. And even though they're the closest morphological analog to Io's paterae, they're very different in lava composition. So what I mean by this is basically the silica content of the lava that caused ash flow calderas is very different than the silica content within the lavas on Io, or the likely silica content, because what we think is that Io's lava is very mafic to ultramafic, meaning very silica poor and low viscosity, so very flowy. And I talk about viscosity and silica content in a different Io video that I'll link to the top right if you don't know what that means. Whereas Earth's ash flow caldera is formed by eruption of lavas that are very felsic or silica rich and very high viscosity or resistant to flow. So in terms of viscosity, just imagine something like honey is very high viscosity, whereas something like water is very runny and low viscosity. The higher the viscosity of the lava that's erupted, the more explosive the eruption and the larger the calderas, or at least that's how it works on Earth. But how are Io's paterae so huge if they're low viscosity eruptions? And another major compositional difference between Earth and Io volcanism is sulfur. Both silicate and sulfur volcanism occurs on Io, like I mentioned earlier, and volatiles within Earth lava include things like CO2 and water, whereas those on Io are things like SO2 and sulfur. All of these compositional differences, as well as the morphological differences in terms of the lack of shields associated with Paterae on Io, point to completely different formation mechanisms for Io Paterae compared to Earth calderas. A potential formation mechanism for Paterae on Io hypothesizes that the thermal interaction between silicate intrusions, so silicate magmas coming up and interacting with frozen volatiles closer to Io's surface, could cause plume eruptions where the volatiles are erupted in plumes that remove so much of that sulfurous volatile material that the surface then collapses. So to visualize this, I'm going to show you a figure from the book I'm using, which I'll link in my description below, that kind of shows this in a visual format, which I needed. But basically, the sulfurous volatiles erupt due to heating from below of the molten silicates. Here's the key to the top right. And then these sulfurous volatiles come out and are lost at the surface through eruption because they've been heated from below and rise and go through the surface. And you can see it's not collapsed yet, but then all that material loss, all that volatile loss of the sulfurous volatiles, leads to collapse of the surface and patera formation, but still it's just sulfurous material at the surface, so sulfurous lava lakes. But then if you have continuous activity and continuous thermal interaction and heat transfer, the volatiles are eventually completely driven off, which unroofs the molten silicates below, causing a darker surface coloration as we observe on some paterae on Io. And then you could even have further collapse if magma draining occurs below, like we talked about for some of the nested paterae on Io that might be similar to some of the incremental collapse calderas on Earth and Mars. We can actually see this Paterae evolution through examining different Paterae on Io that are at different stages within this process. For example, the Sovofluctus represents kind of an early stage of this process where the surface has not collapsed yet. You have an area rich in sulfur dioxide and sulfurous volatiles with some silicate or dark black activity in the middle. And then the Granos and Steropes Patera are shallow sloped Paterae formed in an area rich in volatiles where SO2 escaped by plume or flow, and that caused the collapse, but not yet the unroofing of silicates underneath the volatiles. And then finally, Rumoko Patera shows the dark floor of the unroofed silicates that were beneath the volatiles that drove off the volatiles by heating them, thermal interaction, and then also has molting in the surrounding surface due to ejection of these silicates by the thermal interaction between silicates and volatiles. And then the irregular margins of many of these paterae may be due to subsurface volatile flows caused by this thermal interaction between silicates and volatiles. But even though we have all these hypotheses and even these observations that back up our hypotheses, there's still a lot that we don't know about these Paterae on Io and about a lot of things on Io. And some of these things we still want to answer about the Paterae are lava lakes or lava ponds. Are they directly connected to magma chambers below, or are they just filled in depressions? Does it vary? And if so, why? What controls the variability of Paterae on Io, including size variability, eruption style, activity level variability, all these things? Why are there seemingly latitudinal and potentially longitudinal trends and variations in the Paterae? Why is there a correlation between mountains and Patera? Is there, or is it just random? How do mountains form on Io? That could greatly help us answer that question, and we still don't really understand that. Why are lava lakes so common on Io but so rare on Earth? What about Io's interior and heat flux allows this great abundance of Paterae or lava lakes and lava ponds to be present and maintain activity on Io, whereas it doesn't allow that on Earth? And with the comparison of Io to Earth in mind, what can Paterae tell us about volcanism, either modern or ancient, on other volcanically active or previously volcanically active bodies, such as Earth, Mars, Venus, other bodies in our solar system, and exoplanets? I mean, Io is pretty much our only other data point for active high temperature volcanism in our solar system other than Earth. And so we should take advantage of that and study the volcanism so that we can understand it on other bodies, even though they might have been previously volcanically active and aren't anymore. It can still tell us a lot about their history.
So as promised, now I'd like to show you guys a little bit more about this video's sponsor, Skillshare. I first heard about Skillshare when listening to the SciShow Tangents podcast, which I love. And when I signed up for a month free trial, I thought that I would cancel it at the end of the month, but then I fell absolutely in love because they share so many cool skills through so many cool and creative people on Skillshare. For example, I just finished a class by MJ Trong about presentation design for smart people. And as you guys know, I love presenting and getting better with my presentations and being able to present material in a more exciting and engaging way. But they have so many other courses I'm really interested to look into in the future, like GIS courses, coding courses. I really need to learn how to code. I haven't done so yet. But if you guys want to learn any of those kinds of things, you can go over to Skillshare and become a member for free access to all of these courses. Free access to all of the courses. And if you sign up with the link in my description box below, the first 1,000 people that use that link will get 1 month free. 1 month free for access to all of these courses, all of this knowledge from all of these amazing people. So thank you again, Skillshare, for sponsoring this video. And if you guys want to check them out, again, use my link down below for that special offer.
If you guys stayed till the end, you get the treat of knowing what my necklace and earrings are. My necklace is a picture of Io. My earrings are Jupiter with Io, as well as Jupiter with Europa. So fire and ice. And yeah, that's just because I am extremely nerdy. And I just got these for my birthday. And by the time you see this, it'll be way past my birthday. But if you wish me happy birthday in the comments, I won't complain. Anyway, thank you so much. And I'll see you guys next time. Bye.